we started talking about work and energy. I think on Wednesday, actually, we started talking about it first. But today, I want to continue. But most importantly, I want to see that you guys, can do a few of the simpler things that we're going to have to do on this subject. If you don't remember where we started with this, I said to you that work was the way in which we can change something's energy through the use of a force. And I gave you this relationship, which is the definition of work, mathematically. Anytime a force is used to change an object's position, work is being done. That's what it says here. And there's parts of this that, still might frustrate you, but F here represents the force. And dx is a change in position. And this is a dot product. It tells us how much of the force is in the direction of motion. That should already be in your notes. This relationship is written in such a way as to allow us to evaluate systems in which the force isn't constant while the object is being moved. Now, in the last class, I didn't really give an example of that, but you pushing a box likely would be the same situation, because if you were just pushing on a box, it's hard to apply the same force all the time. But imagine something like this. This is a super simple example of a system in which a non-constant force would be acting on an object. What if I had a pulley here, and a rope attached to the box, and something pulls downwards on the other side? This is a great example of a situation in which the force is changing all the time. Even if I apply a constant force here and create a constant tension in the rope, you realize that as the box moves this way, the angle that the force is being applied is always changing. I wouldn't be able to simplify. I would have to use some amount of calculus if I wanted to figure out how much work was done while moving the box across the floor. This is a situation in which the force isn't constant. I don't have to make it that complicated either. What if instead the force was being done by a compressed spring? I have a spring that's compressed, and I'm going to let the box go, and the spring is going to push it. We know from what we did on Friday that the force that the spring applies gets less and less as the spring expands. That's a force that's constantly changing. It's always in the same direction. It's always pushing the box to the right. But eventually, the box will be, come on. The box will be over here. The spring will be, opened up, and maybe the box has even left the spring now. So the force from the spring was becoming less and less as it pushed the box until the box finally left. How much work is done? I'm probably going to have to use calculus for that. Now, we're going to get there. We're going to get to a point where that's what I'm going to expect you to be able to do. But for the time being, I want to talk about situations in which the force is constant. Under those, we change the dx to a delta to indicate the entire displacement of the object. And I'm going to remove the dot product. The dot product tells us that we have to deal with only the amount of force in the direction of the displacement, but since this is a constant force, I'll go ahead and put in that we're talking about the amount of force in the direction of the displacement, which is the cosine of the angle between the force and the displacement. This would also be work done by a force. Now, as we talked about already, multiple forces can do work at the same time, but I also indicated that work is a scalar product, which means we can end up with positive work and negative work. Positive work increases an object's energy. Well, I think this is obvious. Negative work decreases an object's energy. For this semester, our object can never have negative energy. That won't be true second semester. We'll have situations in which you can have negative energy. So don't think for a moment that positive or negative has as much meaning as you think. Positive work, though, always increases an object's energy. That will always be true. And negative work always decreases an object's energy. That will always be true. But how much energy an object has, that might be a story that changes from time to time. And that has to do with the idea of what reference is. How much energy compared to some state. We'll get to that a little bit later. I'll probably save those kind of specifics for something more important. I want to do something real quick with you right now. And I want you to have seen this because it's important that you see this derivation. I'm not going to have you repeat this derivation, but you should know where it comes from. And then later I'm going to have you do it with the integral because that's the one I'd like to see you do. Does everybody understand? We're going to talk about a potential situation. And that situation is for when the net force on an object is unbalanced. You see, we can talk about the net work on an object in the same way that we can talk about net force. The net work on an object would be the total amount of work done by all the forces acting on the object. I'm not going to repeat that 5 times, but some of you probably should write that down. Net work is the total amount of work done by all of the forces that act on an object. It could be written pretty straightforward, like as the net force times the displacement times the cosine of the angle between the net force and the displacement. Just subbing in. Net work is done by a net force. Any combination of forces then. Now, the reason I bring that up is under this circumstance, we know that net forces create accelerations. We could substitute MA in for the net force. Now, here's where I would prefer to use the integral to teach you something, but I'm not going to. In this circumstance, I'm going to remind you that we're dealing with a special circumstance, that the force is constant, which created a special circumstance where the acceleration would be constant. Under that circumstance, we could use motion equations. I want you to look at your set of 5 motion equations. There's one that should appeal to you. Can you look at them for just a minute? Take them out. You should be able to find it pretty easily. That there's one that has 2a delta x equals v squared minus v naught squared. Well, like do a little substitution. Good so far? Now, this has to be 0 degrees. Once I do that substitution, that has to be true. The net force has to be in the direction of the acceleration, and therefore the acceleration has to be in the direction of the change in velocities. So that can only occur when that's 0 degrees. That has to be true. Meaning this acceleration has to be causing this displacement. Once I make that substitution, I can distribute. And I get this result. This result is a very powerful result. And for those of you who don't know what you're looking at, we have a name for it called the work energy theorem. And as I said at the beginning of class, we should prove this using the integral. It would be better for us to prove this using the integral. But we're not going to. It's going to take a little more work than that. But we can take a look at the result. First, a lot of you already know this, but these terms have very specific meanings. If you've ever seen them before, you know they have a name. We call 1/2 mv squared the energy of motion, or kinetic energy. Kinetic energy is the most fundamental form of energy in all of nature. It is the energy of motion. It is the simplest to see and the simplest to calculate. And in many cases, you guys are already aware of this because you learned in chemistry that the average temperature of a system was the average kinetic energy of the molecules. Did you guys learn that in chemistry? I've come to expect you guys not to know some things, but does anybody know the relationship? Did you learn this relationship? I guess not. It's 3/2 times a physical constant, and this constant is called the Boltzmann constant. You don't need to know this from my class, but this is the fundamental relationship between thermal energy and mechanical energy. So you know how fast the molecules are traveling if you know the temperature. This is how they can tell, like, the temperature inside a star. They can't measure the temperature there, but they know how fast the particles have to be moving in order for fusion to occur. So they can work backwards from there to figure out the temperatures at those locations. So this conversion, the Boltzmann constant, shows up in a couple of places in physics. And this is probably the more prominent. It also explains how much energy there is in light. So the Boltzmann constant has some pretty interesting applications. All right, coming back to this. Look carefully at this side. This is the change in kinetic energy, and this is the work done. If you do positive work, the object goes faster. If you do negative work, the object goes slower. Super obvious. But it also means you have a new way of knowing whether work has been done. If we compare this with our base definition of work, you know work has been done when some force has been used to change the position of an object. That's one way to know if work is done. But you now have another way to know. Work is done anytime an object's kinetic energy changes. This is far easier to see. We can't see forces, but we can certainly see velocity. So any change in velocity means that work has been done by something. All right. This derivation is not something I'm going to have you repeat. You need to know, though, where this theorem came from. You have to know that we started here. And then in some point in the future, I'll have you prove it again using the integral function. But we'll wait for that. This is where I want you to do something more pragmatic. And my experience so far today has been that most students have acclimated to this pretty quick, but there were some missteps earlier today. So let's see if I can't get you guys more closely able to do the problem from the beginning. I have a ramp that's inclined 20 degrees, and I have a 5-kilogram box that I want to push up the ramp with an applied force. And let's say that the ramp is 15 meters long, and I want to push the box at a constant speed up the ramp. And just to make this easy on you, let's say that this is a frictionless surface. What is the work done by the applied force pushing the box up the ramp? Like the answer in joules. I'll say it again. What is the work done by the applied force pushing the box up the ramp? I'd like the answer in joules. You have all the things you need to do this problem. If I want to find work, then in this case, with it saying constant speed, probably going to use the idea that the net force has to be 0 for it to move with constant speed. I see 3 forces. The applied force, weight, and the normal force. I asked for how much work was done by the applied force. Well, that's this one. Pretty sure that force has to be at least mg sine theta big. That's the only way the object moves at constant velocity, is if those two are balanced. So, my constant force times the displacement times the cosine theta. Now, I think that should be enough, but I know it's not going to be. But let's try. Does that give you enough information now? Work out a number. I want to see what you got. We're using this force because the net force in the x direction is equal to 0. Are you listening, Zach?
Yeah, I got it.
So the force minus mg sine theta equals 0. So I want to go back. I don't like going back in time for stuff we've already done. The answer is 257. So all of you looking at the 241, so wondering what you did wrong. You didn't punch in your calculator wrong, but you do tend to not think everything through the way you're supposed to. Let's work this out, figure out why you made a mistake. And I'm going to throw out there that as I say things, I try to make sure that I say them clearly. And here's the first thing. This mg sine theta is how much force I have to apply to basically balance the component of gravity down the ramp. This sine of theta is how much of the weight is down the ramp. This delta x That's how far the box traveled along the ramp, a value given to us, right? 15 meters. Cosine theta is how much of the force is in the direction of motion. It's the angle between the force and the displacement. That's 0 degrees. You put in 20 because you saw two thetas and figured they had to be the same thing. But theta is a placeholder. And these two placeholders mean different things. The theta we have here, we've gotten complacent in using as the angle for the ramp. But the theta that's here is a placeholder for the angle between the force and the displacement. We pushed in the direction of the displacement. That angle's 0. Look, there's a limited number of symbols. We reuse them. You're going to have to be able to be accustomed to that. Be prepared. I know you just want to throw the numbers in. Mr. Shelton, give me the equation so I can get to the answer. No, it's not how this works. You'll have to think for yourselves a little bit. And now you're getting 257 joules. So this is the work done by F, 257 joules. Now that I've shown you all sorts of tricks, what is the work done by gravity? There's 3 ways to get this answer. Take 60 seconds. Talk it out with the person next to you. You could reason your way through this if you'd like. I'd like the work done by gravity while the box moved the 15 meters. Negative 257. Is that what you got? I mean, are you working that hard for it? This is the component of the force down the ramp. That's the component of gravity down the ramp. And the box still went 15 meters. What's the angle between the component of gravity down the ramp and the displacement? I'm sorry, somebody said it, but they didn't say it very loud. It's not 0. That's the direction of mg sine theta. And what direction did the box go? That would be this way. What's the angle between those? 180. This should have been mg sine theta, the component of gravity down the ramp, 15 meters, times the cosine of 180 degrees. And if you're just writing that down, that's not the way to do the answer. It's one way to do the answer. What was the change in velocity of the block? I'll highlight what you need to know for that answer. Change in velocity of the block. We just learned that the work energy theorem equals a change in kinetic energy. What is the change in the kinetic energy of the block if the block's velocity didn't change? Oh, that's hard. Maybe I'll have to do this. 1/2 mv squared minus 1/2 mv naught squared. If the v doesn't change there, what does this equal? 0. It's not like the m is going to change. So the net work was 0. If I did 257 joules of energy, gravity must have done negative 257, so the net work is 0. Did we talk about net work? Oh yeah, we did, right? The sum of all the work done by all the forces. Neither of those are ones I like, though. Here's what I want you to do instead. I want you to prove something to me, because you guys are smart, and you want to see all the different things that are going on here. Let's just remove all of this for just a minute. And consider that the box is experiencing the force of gravity downwards, 50 newtons. And the box traveled along the ramp 15 meters. Therefore, the work has to be the constant force of gravity, 50, times the displacement, 15, times the cosine between 15 meters and 50 newtons. What is this angle? It is 110 degrees. Try it. Negative 257. As I said to you before, this class requires that you bring in the stuff you learned before, but you have to acclimate the new stuff in with this. By the way, there was a normal force acting on the box. How much work was done by the normal force? 0. What's the angle between the normal force and the displacement? This angle right here. What is it? What's the cosine of 90 degrees? I'm not trying to trick you. I'm just trying to lay it all out. Box going up a ramp. Not a whole lot of stuff here, right? By the way, what if the box started at the top of the ramp? I mean, what if I started the box at the top of the ramp and just let it go? There's no friction. Can we agree the box would slide down the ramp? Can you tell me how fast it's going at the bottom? You think this is going to be a lot of things to do, but it's really not. How much kinetic energy will it have at the bottom? Aw, this isn't hard. If we push the box up the ramp and it took 257 joules to get there, and I let it go, how much work do you think gravity's going to do bringing it back down? Yeah, so the work done is going to have to be 257 joules. I think all that's going to be right there. Some of these questions are not challenging. You're just seeing them for the first time. You need more practice. Of course, that means like 50 homework questions. That'd be the best way. Do every possible permutation. That way, I feel as though you've done your part. And I will run out of time before we get a chance to totally evaluate this, but you should begin thinking about it. Let's use the same box, and this time we'll just put it on level ground. But this time, coefficient of kinetic friction of 0.3 between the box and the ground. And let's push the box the same 15 meters along this level ground. I'm thinking of 3 questions, but I'm only going to ask one. How fast is the box going after it's moved the 15 meters? You have lots of ways to do this question. You could find that force. You could use that to figure out acceleration. You could use a motion equation. But I'd like you to use the work energy theorem. Here's what I'd specifically like you to figure out. I'd like you to find the work by the 25 Newton force. How much is that? And I'd like you to find the work done by friction. How much is that? I'd like you to use that to figure out what the net work is. How much is that? And then that has to be equal to the change in kinetic energy. That's what I'd like you to do. I mean, I'll tell you the answer. It's like 7.7 meters per second. I want you to try this route. I tell you, it's super straightforward. Now, there's only a few minutes left. Try it. See what you can do. The bell rings now, but the answers are there. See if you can do it.